today I'll talk about kind of very fundamental issues on the concerning about the variation inequality and how to solve the system with constraint. And we know almost all of us know about name of the interior point method, and it said that the matrix becomes singular in some extent, but I found it's not true. So I'd like to explain that. And then I'd like to I think about.
Share your screen on the people.
Sorry. I have to share the screen. Yeah, it's okay. So maybe just a moment. I have to small this one, and this is called.
You should go to more. You can disappear.
Okay. So it's maybe I think this is so, or just as in the case of the eye, it bit smaller. It's better. So it's my talk is very fundamental. So maybe almost no person knows, but I'd like to emphasize my purpose to. I'd like to keep the finite element, FreeFEM script to work with other than linear solver. So yesterday, Frederick said that there is no non-linear solver in FreeFEM.
Yeah.
But the FreeFEM is designed to create the stiffness matrix from the variational formula. But then also the PL is essentially work with connected PETC. And PETC can handle almost everything. But sometimes I think there is some space to be optimized more. So just past 5 minutes. So then is my first topic is to think about the kind of variation inequality for obstacle problem, and this is written by kind of the fundamental stuff to find the minimizer to project on the convex set, the closed convex set. We know the mathematical there is solution, but the question is there is no way to construct the good projector on the closed set. So we have the other way to solve the problem, introducing Lagrange multiplier. And the famous one is active primal pure active set method, and also semi-smooth Newton method. And that is the two subsets almost equivalent. But another way, complete another way, is to think about quadratic programming by interior point method. So here is I will show first of the code for FreeFEM to primal pure active set method. We can control the mesh refinement during iteration. But quadratic programming is just a black box solver. We will give the matrix. And I think there is maybe, if we call the black box solver, we have no chance to play with the mesh refinement. But I'd like to keep that inside the FreeFEM code. In that case, there is possibility to work with mesh refinement internally of the iteration. That is inspired by a program of the cavity flow by Navier-Stokes in the FreeFEM code. There is a combination of mesh refinement and Newton iteration. So we can proceed with nonlinear iteration in sense of the continuous level. So that is then is we can apply the mesh refinement. So the purpose is that. So for that, but anyway, we have some difficult matrices in the indefinite system by primarily interior point method. And also this is said the matrix becomes singular. So I'd like to explain what becomes singular. First is to be clear the problem. I will think about very simple Poisson equation like one. And this is Poisson the linear formulation. I would like to minimize energy of the quadratic form. And the constraint is value of G is something below some predefined physics-style value. So the K is a convex set, closed set, but not space. So the variation inequality to find is this form, and this is the complete equivalent to the minimizer to find the minimizer of U on the closed set. So if the K is closed, we know this is a unique solution. But the question is how to solve this. So typically we have the like that. So here is threshold on the top. There is the Poisson equation. I'd like to put the top of the limit of the top of the space, the figure. So this is the figure of Lagrange multiplier. On the top is U minus G is let's say that is U equal G is set. So constraint is in the dual space, that is, that we have the variable Lagrange multiplier. So it's so-called the complementary constraint is satisfied with some constraint of the unknowns and the limitation, and times the Lagrange multiplier becomes disadvantage. That is the constraint. And here is if I can combine mesh refinement to watching of the some smoothness Lagrange multiplier, I can define a mesh and I can get the better solution. This one is based on active primal dual active inactive set method. Method. So this is method A is active set is improved by step by step. So the basic idea first is I'd like to just briefly show as we talked with this is by form. And then in this case, it's the function the solution is found in with spacing without constraint. But here is we need to find the solution in the convex set, and minimizer is found. And this should be converted to kind of the problem is like to unconstrained problem. But here is only found solution and test function is only found in the set of K. Then is the idea to introduce Lagrange multiplier. And lambda is the if we define the active set and inactive set. So in the case of the active set, that means the constraint is completely satisfied. In this case is I can sorry not yet here sorry, but maybe is first stuff is I need to explain this integration, but the first one is I can write this equation with Lagrange multiplier. So here is a standard division form, and this is Lagrange multiplier. And solution should be found in the in subset. Then is a test function is in the whole space. And this is just I would like to change to this K to the whole space. In this case, is just I put the constraint and Lagrange multiplier and complementary constraint. And complementary constraint is the first is expressed by total integration over the omega. But this can be separated by using the active and the inactive set. Just is has a problem as integration has meaning on only active set. So this is one strong tool to solve the variation inequality. So the idea is to take it further. So if we could introduce nonlinear relation using parameters C, lambda can be expressed. The complementary condition is expressed by this one. Lambda is it should be equal to the maximum of 0 plus some constant conditions. And then here finally we will have this condition is much more simpler. So the simpler means in only one equation. The u minus g, u is less than g is satisfied, and then complementary condition that is almost equivalent to the Kuhn-Tucker condition is satisfied. So this is a way to derive kind of a semi-smooth Newton method. And semi-smooth Newton method is once eliminate of the polynomial form A, we can eliminate the primal value u, and then just lead to the dual problem. But this is max is not differentiable, it's not smooth. So this so-called semi-smooth Newton method is can deal with, and then the analysis of the convergence is already done. But practical way we can use so-called primal dual active set method that can iteratively update of the active set. So this is shown in the example of the FreeFEM code, so the tutorial of the documentation is obtained. We can define first the dual active set, and we solve the equation. And then to update active set, we measure of the similar condition of the around lambda plus some parameter c. And this is a case new parameter is defined by dealing with this kind of the measure of the difference of the constraint and the unknown variable. So then we can update. So this method is written by continuous form So there is space to introduce the place to introduce kind of the mesh refinement during integration. So actually the code we can write in this way. But here is we need to solve the personification with boundary condition on active set. That is we need once since we have to make mesh refinement. But the idea is to introduce kind of penalization. We don't need to use the mesh refinement, but is written by already on the tutorial writing. So it's just a standard definition of the value. That's okay. So to do update that one, we have to modify of the stiffness matrix by penalty according of the active set unknowns. This is a AII taken from the diagram, and this is modified to put the internal boundary on the so then the duality is computed by the original matrix that is correspond to the integration of the that's the kind of correspond to the Euclidean number. We can get the Neumann data. But here is to work with this way, if we can work with a single process and then direct solver, there is no problem. But the difficulty is how to parallelize or how to apply another linear solver. So this way is just we can get good result. Already I showed, for example, I showed this one. So this is obtained. But the drawback is this looks like the standard linear system, but due to the penalization is a little bit far from the standard way. And also I already said that we have some good steps to introduce mesh refinement, to looking of some distance of the using information of Lagrange multiplier. We can introduce some mesh refinement. So this is the result. But I'd like to introduce the completely sorry, to do that much. I will summarize the equivalence of the active dual set method and semi-Newton is already shown. And that means gradually we have the good relation to this deep working. But I'd like to show kind of the quadratic programming. So instead of the modifying of the stress matrix, just working on only with the Lagrange multiplier. So 10 minutes. Okay. So here we have the energy minimizer, the same of the K, and after discretize, I have vector. And this one is written by the constraint is written by like that. So this is exactly the same to Kuntaka constant is Lagrange multiplier is positive. And then new minus G is the take in the product lambda new minus G is there. But the issue is we need to solve this one. This is just condition to guarantee of the solution of this minimizer. There is nothing to be said to how to solve this one. Then is the idea to work with so-called interior point method to find the data inside of the feasibility set. So to do that, we would like to introduce so-called barrier function, that is penalized of the constraint. And energy is penalized. Here is the one parameter mu, and this is target constraint. G minus U is constraint. Target is minimize the energy. Then there's we could formulate instead of the minimization problem on the constraint set. This is a new energy form in whole unknowns. So of course we have to control mu k, but hopefully is if this algorithm is have solution and the mu k goes down to 0, we can prove that the minimizer with satisfying constraint is found. So the argument is completely the discrete level. So here how we can extract the algorithm. That is the sense of my talk is how to understand the linear solver. What is difficult here? So this is nonlinear minimizing problem, and I can take the extremal by taking derivative, taking variation. So here is J is corresponding to A minus F, This part is logarithmic, but if I take the variation view, just the logarithm is changed to 1 over something. So this is C inverse is diagonal entries of this price. So this is just taking the first derivation is I can get to the A minus F plus mu C this diagonal matrix and times 1 x equals F. So this is, of course, is important here. If we make derivation of this constant C is taken by the with minus identity. So this one is extremal, and I have the point of the Newton iteration to do that. So case of to solve the system is I have to solve this equation, but first I need to introduce this is nonlinear system. A better way to introduce a dual variable lambda. So this system is written by in 2 lines, AU minus F plus lambda. This is linear system, and this is constant is 1 over U. That is nonlinear stuff, and this should be solved by Newton iteration. So this is completely unconstrained problem, so easy to implement. And also by taking just apply Newton method, so we can get natural discrete sum taking of the Hessian of J, and then the taking of the second derivative of the logarithm. So that we can get to the C minus square divided by twice. And the right hand side is the residual of this nonlinear system. We have the Newton method. So this one is the Newton method. So then is how we will solve this one. This is the big question. So this one looks not much like symmetric, but your sense is once we multiply C here, we can avoid C minus squared. Then just the 1 over C, and C is separated. Because this mu times C is correspond to the complementary constant, and the Lauder multiplier is obtained by this way. So if we have the separate C square, it's a little bit problem. So what is the problem is it said that is why the interior point method suffering of the bad constant number is comes from here. If we eliminate of the dual variable, so this matrix become like that. So A plus C mu C square minus. This become bad. We can fix of the mu C is some constant, but the C, if the C is C of the constraint, it becomes 0. So some part of the diagonal entries become infinity. So if we do the extraction of the dual variable, we can get to the smaller size of the matrix, but constant number become bad. That is natural way. But the good news is that it becomes a positive semi-definite matrix. Unless people try to use this one, and also the tau type IPD IPopt into the setting, and IPopt to follow the same way. But essentially, this implementation is difficult. So the idea is just solve directly this system. And also the other one is try to also change the sign again, but this is also become indefinite. The analysis is done by 1996, but I would like to try to use this one directly. So to do that, I need to some kind of strongest direct solver can deal with indefinite system with proper pivoting. But fortunately, if this system is always invertible, whenever happens, because of the structure like that. So some part of the complementary constant becomes 0, but some part remains, and thanks to the decomposition of the active and inactive set, we remain of this decomposition, and this part become invertible always. So, there's no influence by the convergence state. So the writing is simple like that, thanks to the block matrix. So the condition is I can define the diagonal entries U minus 3. And this is a bit tricky to treat with my negative sign. So I have to define the something originally G minus written, but I cannot apply minus C inside the matrix, block matrix. A little bit tricky. And also the vector computation is times minus 1 that appears. but this line is instead of the active primal active set method. Then is for example convergence like that. So this is the same parameter as the simplest case of tau. It's I set the parameter for the barrier function is 1.0 and decreasing by factor 0.1 if converged. So this is my book. Then, of course, if I directly I talk to much simpler, but this line is so much defined. And then, here I didn't show the place of the mesh refinement, but I can deal with directly the Lagrange multiplier here. So I can combine with mesh refinement. So this is the summary. So variation inequality can be solved by kind of the interior point method combined. And if we can write the strict FreeFEM script directly, interior point method is allow is introduce mesh refinement. So this is it. So maybe that is we can apply parallelization is but that's by hand. So the last one is just a few minutes. I have the.
You can show the.
But unfortunately, this one is website is closed. I have the 3 days lecture in Japan in January weekend, and material will be shown in the website. And this year's purpose is to I'd like to talk about the Pierre's idea with combined with PETC to FreeFEM and use how to easily access PETC. Before that is I would like me to explain how directly work play with PETC is slightly difficult, but through FreeFEM it's very somewhat easy. And also the next step is 4th week is I implemented FreeFEM on Fugaku, the supercomputer 64FX. Unfortunately, is not allow dynamic loading. I have to prepare the object which is already linked with some libraries, but now it works. So people with the join of the lecture, so they enjoy. And I have another meeting on the middle of the February. It's a small workshop in this is only in Japan, so but it's activity in Japan. Thank you, your attention.
Remark, comment?
So I think a couple of slides before you mentioned that you need to do asymmetric solver with pivoting.
Yeah.
So are you using dissection for this?
Yeah, this Paradis or Mampus is okay.
Okay.
But I'm not sure about the super dist. But now is Paradis is not works on the Intel the ARM architecture. So why is I'm carrying a small Mac mini? This can work is in Paradis.
I can see you dealing with a very hard problem. Apart from the Poisson equation with the constraints, do you have other applications like slightly more complicated constructor problem? Or...
Yes, that's great. Because originally, I start to work with shape optimization and calculate the sensitivity and moving shape according to sensitivity by solving the elasticity problem. But sometimes that is movement some extent of the boundary. I put the boundary condition is inside, the movement is not exceeded some limit. This is some motivation to.
It's very hard. Problem.
Not so hard, just of course that is just not physical meaning. That's tricky on just for numerics. I'd like to the limit of the space position of the moved boundary is less than some part. Just is exactly same to the constraint. The Poisson equation just moved to the elasticity, but essentially same.
When you make the Newton iteration, do you have to reduce the step or not?
No, is this very simple case. I don't need anything. Just mu is smaller. A Newton method is just directly apply to using the previous step. First step is not good. But the second twice after step is a Newton method not much here. Just maybe probably is too simple.
Okay. So thanks again.
Thank you.